Okay, so let us do this problem by flexibility method. This problem is one with a portal frame having support settlement. A portal frame ABCD with a support D settling down by 10 mm, and also it is having nodal loading as well as span loading. This same problem the other day last week we have done using stiffness method. We know how to do it using stiffness method. The same thing will be repeated to attack it using flexibility method. So the problem is very clear. A B C D. Okay, 50 kilonewton at B nodal load, 100 kilonewton at beam B on beam BC at a distance 2 meter from B, and settlement is 10 mm for support D. No other settlement and nodal loading or span loading, applied loading only. Uh, then to calculate EI value, column dimensions are given 300 by 300 column dimension, and beam dimension is 300 by 450. Now that 300 by 300, you know EI value. Beam depth should be taken as 450, not 300. That's all common understandings or knowledge. So E is also given in the problem. So you can calculate EI. I have calculated EI to be used in the flexibility matrix. So EI for both columns are 16,875 kilonewton square meter. So in useful units, you have to convert it. Another column CD's EI is also same 16,875 kilonewton square meter. EI of the beam is 56,953 kilonewton square meter. So those things are straightforward. Now the issue is how to deal with the support settlement in flexibility. We should remember that in stiffness we have converted the support settlement into equivalent moments, isn't it? So that is a way to do in stiffness method generally, because support settlement like translatory settlements in stiffness method, our coordinates are generally active degrees of freedom, so they are generally rotational in nature, and at supports generally we don't have those degrees of freedom, so such coordinates we don't select. So that's the reason why we convert that support settlement into moments by using the conversion formula which is available even in slope deflection equation, minus 6 ei delta by L square, those formula, so that we remember how to do that. Now here in stiffness method, we have a scope of directly taking that displacement or support settlement or prescribed displacement into the displacement vector. You remember in flexibility method we have three types of displacement vectors. If you remember that, then only you can proceed further with this video or understand the video further. Those are small q, small x, small r, where small q refers to element level displacements. In flexure, it is the rotations at both ends of the flexure element. Small r is the displacement corresponding to wherever we have some applied loading, and small x is the displacement corresponding to the capital X. Capital X is the redundance. So we remember we have capital X, small x, capital R, small r, capital Q, small q in our formulations. So it is always better if, so far as possible, it is better to take the support settlement into small x vector. How to do that? Try to assign one of the redundants towards the support settlement direction or location where support settles. In this particular problem, at support D vertically settles down. So try to apply a redundant in a vertical direction D. So we know that we need to remove some redundants. So remove at least that redundant in that direction. And in this problem further, you need a primary structure or statically determinate one. We have two fixed supports, three extra, ds is equal to 3, so we need to remove three reactions, so three redundants. So it is preferable, our earlier objective also will be achieved if we remove support d to make the primary structure. So in that case, that's a fixed support d, so we have various reactions including the vertical reaction. So the support settlement 10 will come into the small x vector directly. So our formulation is quite easy. So this is a principle to be followed. Always look for a possibility of taking support settlements into small x vector or redundance direction. Or redundance shall be designed by keeping this in mind, or defined by keeping this. This is what we should do. I will explain further. See the global coordinate I have selected. I have removed D, and the global coordinates are 1, 2, 3. So 1 is a vertical, that is corresponding the vertical direction at, vertical reaction at D. 2 is the horizontal reaction possible at D. And 3 is the moment reaction possible at D. So in this particular problem, our support settlement 10 at D is directly along coordinate number 1. So we can take that 10 directly into small x. That is our goal. We need to, or objective. Not that goal may not be always achievable. So that should be our objective. If at all it is not possible, then only we need to think about taking it into small r coordinate, and how to deal that case where support settlement etc. is in small r. I have discussed that in the previous problem of the truss. Same formula applies here also. But anyway, in this particular problem, we will be we have the opportunity of taking 10 settlement into small x 1. So directly in the solution equation, what is the solution equation? Capital X equal to f x x inverse x initial or x minus fxrr. This equation we have derived. So what I mean to say is that we can directly keep our 10 settlement in this particular vector. No other further modifications etc. are required. So that is our objective. So, and also we have the nodal loading and span loading. So nodal loading has to be taken directly, no change in direction, etc. But EJL is the reverse of fixed and moment. Here only moments will come, not fixed and reactions will come. You know that we our coordinates are like that only, and also you know about our local coordinates: 1 star, 2 star, 3 star, 4 star, 5 star, 6 star, and you know about our flexibility, element flexibility metrics corresponding to this particular local coordinate system. So in global R coordinate, we have used the EJL. Okay, EJL 88.89. That is 100 kilonewton is acting on BC. So 100 into 2 into 4 square by 6 square. That is anti-clockwise in a fixed beam. It's reverse. So this is clockwise. We have applied 88.89 is clockwise. Similarly for end C, it is 100 into 4 into 2 square by 36 or 6 square, that is 44.44. That is clockwise in a fixed beam, so we have applied the EJL as anti-clockwise here. So 50, 88.89 and 44.44 as the EJL. So everything, every initialization we have done. Now we can go to the uh, usual formulation. So for this we need BR, BX, F star, etc. Triple product for F, then solution. So BR, BX, see BX, I have selected this as I have mentioned. So coordinate number 1, 2, 3, 1, 2, 3 towards X. That is in BX it should come, and BR is coordinates are 4, 5, and 6. Okay, coordinate 4, 5, 6. So based on this coordinate system, we need to write our BR and BX. So BR, BX, I have shown you the three columns diagrams corresponding to three columns. Column number one of bx, column number two of bx, column number three of bx. I have shown that here. Okay. Now it is shown. Now the equilibration. You need what all you need to do is simply equilibration. That is only the task. So it can be easily done. Just a minute. I don't know, some memory issue. So it is slow. Okay. So Bx direct straightforward equilibration. Br also actually it is so you write Bx here. Okay, some error. This one should be yeah. It should not be zero. It should be one. I have corrected that. Then Br we have 4, 5, 6 coordinates. So I have shown all the three diagrams corresponding to BR. This is column 4, this is column 5, this is column 6 diagram. So just find out the equilibrations. Element equilibration you do segment wise or element wise, then what you are going to get is this matrix. So this is Bx, this is Br. So these are straightforward. Anyway, still I'll be anyway discussing the column 5 and 6 for you because some of the students always have that doubt in column 5. This is the free body diagram corresponding to column number 5. This is the primary structure. And for column 5, you need to apply coordinate 5. Coordinate 5 is applied with a unit moment here. So this what happens to the students is they will have a doubt. This one, how it should be distributed among 3 star and 2 star. That doubt they have. Similarly, in the next column number 6 also we have the same issue. Column number 6, this is the primary structure, same primary structure, same primary structure. Now, there we have a coordinate 6 unit moment in the reverse direction. Coordinate 6 is anti-clockwise. Here also students will have doubt how this one is to be distributed uh, among 4 star and 5 star. So students have doubt. In this case, there are many possibilities. Shall I take 4 star equal to 1, 5 star equal to 0, or 4 star equal to 0, 5 star equal to 1? Okay, or 4 star is equal to 0.5, 5 star is equal to 0.5, or some other combination. So that is in the case of column number 6 as well as column number 5. So that I would like to explain because some of you have that doubt. So column number 5, this is the free body diagram. Okay. Now this doubt occurs whenever your moment applied is at an intermediate joint. Here joint B. If it is at the end, for example, in Bx column number 3, that is this diagram, there is no doubt because that blue curved arrow, that is the moment corresponding to coordinate 3. Okay, this one, it is at an end, so there is no doubt in equilibration center. In this only you have doubts. I'll explain that. What you have to do is, of course, by drawing this diagram, you cannot decide the quantity divided into 2 star and 3 star. That is not possible. No method available. So you have to start doing the equilibration. When you start doing the equilibration, it is preferable that you follow something like this. See, 1 star is applied clockwise, so support reaction should be only one support is there at A. D is supportless, so A has to carry that equilibrating moment. So that is anti-clockwise, isn't it? Anti-clockwise 1 because applied is clockwise, so anti-clockwise 1. Okay, now what to do for the rest? So this is actually 1 star is now clear. 2 star is still you have doubt, or otherwise you know that for equilibration of this vertical member AB, this is member AB, you need to, because this is anti-clockwise, so one clockwise moment should be there at the 2 star. So this is a way or hint. So what you have to do is this applied is also clockwise. This is also clockwise. So remove this, or this is this, or the applied moment is now 2 star. With that hint, now you can write 3 star. What is 3 star? Naturally, the sum should be applied unit clockwise 1. So this should be 0. Then only 2 star plus 3 star will become 1. If you write 3 star as again 1, then 2 star plus 3 star will be 2. That is not there. So 3 star is 0. Now, how to go to 4 star? 4 star is, of course, if you check the equilibrium of a beam BC, naturally 4 star has to be 0. Or otherwise, what you can do is you can start equilibration from this end. This is a free and no moment here, so this one, that is 6 star is 0. This also should be 0 due to that 5 star. This also should be 0 due to 4, 4 star. So like this, there are many ways of doing it. I have displayed one way, which is quite easy and straightforward. So that is how you transfer this. Okay, so what happened is this unit moment is transferred to 2 star in order to keep the equilibrium. Of course, it is, I have just used the term transfer. It is not actually transferring, etc. But just to understand the procedure, I have named it as transferred. Actually, that is a result of your equilibration. Similarly, the column 6, or that this fellow 6 unit moment. So you can now simply say where to transfer this, how to divide it. There is no division, because if you start from this end, this is 0, this is 0, naturally you know. So this is 6 star is 0, 5 star is 0, naturally you know, because there is no moment here, this is a free end. So naturally this transferring will be to 4 star. So you transfer this to 4 star. Same sense, 4 star is now unity because anti-clockwise. So this you got. Then you can complete that equilibration. So this will be naturally clockwise. This will be naturally anti-clockwise. This will be naturally clockwise, like this. And you can cross-check the support reaction. Whenever a unit anti-clockwise moment is applied here, any location, the support reaction should be clockwise one. That also is matching. So by using this methodology, you can easily draw the free body diagram and easily write BRBX whenever you have unit moment at intermediate locations. If the unit moment is at an end, there is no issue. And also, when translatory force is at an intermediate location, there is no issue. You can take the support reaction and proceed further. Only issue occurs with moments. So that's why I just explain. Anyway, I need not to tell you all these things, because you are also experts in drawing the free body diagram, in calculating the forces in a free body diagram. You are experts, but still, I'm just telling you to a method, one of the methods only, to how to do it faster. That's all. So, as a result, from this diagrams, you can write this particular matrix BR, column number 4, column number 5, column number 6. Then everything is straightforward. Then you write F star, find out the triple product, FXR, FRR, etc. etc. F star, you should know that globally aligned one should be, arranged one should be a 2 bandwidth. We remember that F unassembled for axial was a single bandwidth matrix, only one element. Here it is, that was every element L by AE, L by AE, L by AE diagonally, and all others are 0. Here it is a double bandwidth, or two lines will be there like this. For each element you have a 2 by 2, next element you have a 2 by 2. So that is a structure. Such things are very easy to remember also, like this as a pattern. Okay, isn't it very beautiful pattern even? Or otherwise 2 by 2, f star is something like this, 2 by 2, like this for first. So it is 2 minus 1 minus 1 to inside this square. Second element is like this, 2 minus 1 minus 1 2. Third element is also 2 minus 1 minus 2. Fourth also, if four elements are there. Here we don't have that. Anyway, we have only 3. So like that, it should continue. 2 minus 1 minus 1 2 multiplied by L by 6 EA. L by 6 EA of the L by 6 EA of the corresponding member. So those things are just as a freshing up. I have just explained. You know these things. So I have written F star unassembled matrix. 79.12 is taken from our EI value. EI value already I have evaluated, and 10 raised to 6 is taken outside for, it should be 10 raised to minus 6. See, L by 6 EI, isn't it? So it should be minus 6. So that is taken outside. F star minus 6. Then triple product naturally. Fxx, Fxr, Fxx is Bx transpose F star Bx. Fxr, these are the two we need. And also, last problem we have seen, we need FRR also, but when it is required, FRR is required if we are taking our displacement or prescribed displacement or support settlement into smaller. In that case, you need that. But here we don't have that, so no need to calculate FRR, etc. Don't waste time. So if you have an overall idea about the method of formulation, then your time can be saved, or otherwise unnecessary you will calculate all the metrics, etc. Okay, so FXR is Bx transpose F star Br. So I have taken 10 raised to minus 3 outside. Previously it was 10 raised to minus 6 in F star. Now minus 3 outside to show that in a better manner. Now, as usual, you know the equation. So target the equation and do. You know the equation. Capital X is equal to fxx inverse x minus x initial minus fxrr. If you remember this equation, this is your target. So you need r also. So r is available. Coordinate number 456. It is as per EJL. EJL direction itself is taken as coordinate direction. So every element is positive, positive, positive. Okay. Now we need x in E here. So x in E directly, because coordinate number 1, you have 10 mm settlement in the opposite direction. Coordinate 1 is upward, but settlement is downwards. So minus point not 1, that is 10 by 1000 in proper unit. So this is meter is the unit. 0 0, because there is no settlement for 2 and 3. So minus point not 1, 0 0. So once you make all these things, then you target this equation and solve. That's all. So here fxx inverse, I have written inverse directly here, multiplied by x in x initial is written here, minus point 100 x initial. Then fxr, I have taken this one, fxr, r is 5088.89. So complete. Your capital X is now solved. So capital X coordinate 1 2 3, you are getting 20 minus 36 minus 77. So there your solution is over, but you need to go for post processing in order to get the member, this one. So wherever your inversion occurs, that is the solution. Okay, inversion equation, or wherever the inverse matrix comes, That is the solution step. After that, you need to go for post processing. So Q is, you know that Q is equal to BRR plus BXX. These are all straightforward. BRR, you know, BR is available here. This is BX, this is BR. BR multiplied by R is 50, 88.844. So that multiplied, this will result. Then BX is available here. X we have already solved. Three values were there. So if you multiply, you are going to get this value. Add them, you are going to get the Q internal moments. But that is not the final one because you have used DJL. So that has to be taken out. So add a FEM to that. So Q final member moments, 1 star, 2 star, M1 star, M2 star, M3 star, etc. is Q plus FEM. So Q this you got, then FEM is uh, the 100 kilonewton fixed end moment, as we know 100 kilonewton. This is the fixed end moment here. This is fixed end moment 88.89, and this is 44.44. This is anti-clockwise, so negative or just the reverse of EJL. That's all. So minus 88.89 and 44 is clockwise. So our coordinate number 6, that is actually global, but this is FEM at coordinate number 4. 4 is also clockwise. So clockwise, so plus sign here. Don't compare it with the global 6. This is local, I mean, metrics. So add them. All other, even 15 need not be taken. 50 is a nodal force. No FEM corresponding to that 50. So only 80 minus 88 and plus 44. So add them. You are going to get, this is the final result. So once you get, these are all moments, isn't it? Then you can draw the bending moment diagram. So bending moment diagram, this is negative, negative. So in this particular, this one, minus, minus means on the opposite side. So this should be the bending moment diagram for this one. Then plus plus for the beam BC 7 and 69 plus plus. So that also will be on the opposite side. And also you can check this joint moments cancel each other. 2 star, 3 star is at the joint, you know. 2 star, 3 star is at the joint. They should cancel provided you don't have any nodal moment initially. No nodal moment in this particular problem. You have only nodal force, no nodal moment. So there is no, they should cancel. So minus 7 plus 7 cancels. And this diagram, same plus plus. So the diagram should be on the opposite side. Okay. Then for the column minus 69 minus 79, same side. Okay. Minus, not same side, opposite side, same sign. So opposite sides. Okay. And this also is cancelling joint. There is no nodal moment applied at C. So C's moment, my 69.8 and minus 69, they are cancelling each other. So like this, and opposite side you can draw complete the diagram. This is not complete. You have to add the 841. This is 77.213. This is 69.8. This is 7.1. Then you superimpose the something like this to free BMD due to 100 kilonewton. Superimpose that. Okay, that's all. Nothing else is required because 50 is moment is not to be, this 50's moment need not be taken. There is a nodal. It's already came in our solution. So that is the final Bendimon diagram. We can draw that. So with that, we finish off um, flexure case with the support settlement. So I have told you the principle. Always try to incorporate that support settlement into small x coordinate. That should be your target. Okay, in university exam problems, generally one or two settlements only will be asked, so that can be comfortably taken in small x. But whereas if in a problem, if all the supports are settling, that also is possible. If all the supports are settling, then you cannot have those all settlement in small x vector. Then what you have to do? Go for the balance into smaller vector and convert that to x ini, as I have told you in the last problem, and thus you solve. Okay, thank you very much. This is all about flexibility of vector. So you can extend the same formulation to a beam, continuous beam. Extend. It's only matter of extending. No, it's not a new problem. Same, apply the same principle. Suppose you have a continuous beam, two or three redundant supports, and if one of the support is settling, so include that into the x coordinate, that support reaction, or remove that support where the settlement occurs. Remove that, then automatically one redundant will pop up, x1, x2, x3, etc. So same principle, nothing new. Try to extend this to that also. Okay, then, thank you.